Hey everybody, it's Mr. Oliver again. This video is going to be the solutions for the Unit 2 uh, end of year practice on Newton's laws of motion, and this is for AP Physics C. I will just say that this video might run a little bit longer, and also in some of the calculations, or actually in most of them, I'm going to use uh, G as 10 meters per second squared instead of 9.81. It just makes the calculations a little bit easier, and you're allowed to do that on the AP exam if you'd like, but unless it specifically says otherwise. But anyway, let's go ahead and get started, and here we go. All right, so this first question says the maximum amount of mass that can be hung vertically from a string without breaking is 10 kilograms. So that means that if I hold this on a string, the most mass that this can be is 10 kilograms right here. And so that means that the force pulling down on it, of course, would be mg, which would be 10 kilograms times 10 meters per second squared. If remember, I'm making that assumption that that's going to be 10. And so we've got 100 newtons that this string right here can have before it breaks. So the question says that we're going to hang a 0.5 kilogram object on the end of a string, and it's going to go in a circle. So this is going to be a kind of a centripetal force kind of problem. So if I have this circle and the object is going to be on a 2-meter long string right here, 0.5 kilograms, that's how much mass this thing has, then we need to find out how fast you can spin this without it breaking. So we're looking for a tangential velocity to be able to calculate a breaking strength of the string. So this is pretty straightforward. We just say the centripetal force will equal this 100 Newton braking force. All right. And if you remember, centripetal force can be calculated by taking the mass times the centripetal acceleration, where the centripetal acceleration is just the tangential velocity squared divided by the radius. So all I need to do is set this expression right here equal to my 100 newtons. And so after you do that, 100 is going to equal 0.5 times Vt squared divided by 2 meters. And when you make that calculation, you end up getting square root of 400, which is 20 meters per second. All right, and that's the maximum speed that we can rotate that object at. All right, our second question says we've got a particle mass m starting from rest and moving along a positive x-axis under the influence of a single force. So the idea here is that we've got some object being pushed with this force Fx. All right, now in this case, that force is not a constant force, it's a linear force. If I were to graph that force versus time, that force is increasing as I go along. So I want to know what the velocity of the particle is given, what the velocity of that particle is. All right, so in order to get the velocity, I need to understand that the force, which is equal to ma, this horizontally applied force, I can get a velocity by taking the integral of the acceleration, because remember, the velocity, change in velocity, is the integral of the acceleration with respect to time. So all I really need to do to get A is just divide my applied force divided by m, which would be bt divided by m. And so that's my acceleration right here. So I'm going to make that substitution for acceleration and take the integral. So delta v is going to be equal to the integral of my acceleration, which I said was b over m times t, and I'm separating this out because b and m are constants, and I'm integrating with respect to time. Now I do need limits on this, so I'm going to go from the time of 0, because that's where I'm starting to some arbitrary time later, which I'll just label as t. So when I take this integral, my delta v will be equal to b over m times the integral of t dt, and the integral of a variable. This is like raised to the 1 power, right? So this is going to be t squared divided by 2. And when I evaluate it between 0 and t, of course the 0 term will go away. And this is going to be my solution right here for my change in velocity. Now it is actually a little bit careful. You got to be a little bit careful, because unless you understand that the change in velocity, which is v final minus v initial, you might get in trouble a little bit, because it does say it starts from rest. So luckily this initial velocity term right here, this initial velocity term right here is 0. So our velocity as time goes along will just be this bt squared over 2m term. So just be real careful when you take this integral. Remember, this integral is a change in velocity, not just velocity. All right, next question. We've got a system of blocks A, B, and C, and we're pushing it with a force F. And so this is a pretty straightforward question. Just remember that this force is going to accelerate block C, which then accelerates block B, which then accelerates block A. So this system of blocks you can just treat as one object. So what we need to do is we need to say, well, what force has to be applied to accelerate the 3 blocks at 2 meters per second. So let's do this real quick. Let's just say F of the system. Remember, this is our little trick that we do for systems of forces, is equal to the total mass times the acceleration. All right. So this acceleration right here is 2, because we're going to accelerate the 3 blocks. Our total mass is 3 plus 2 plus 1, which is 6. So that means that this force on the system has to be 12 newtons. 6 times 2 is 12. Okay. So if I'm applying a force of 12 newtons here, then if you kind of consider what's happening with this system, this 12 newtons has to accelerate 3 objects. So you got to think, okay, well, how much force does each individual block have? Well, if I push on this block, it's only accelerating 12 newtons, or 6 kilograms. That is not necessarily the amount of force I need to accelerate this, because this block C pushing on block B only has to accelerate 3 kilograms. And so there'd be 12 newtons here pushing on block C, which is what it's asking. But how much force is needed to push on block B? Well, I've got 3 kilograms that I'm going to accelerate at 2 meters per second. So 3 times 2 is 6. So there'll be a 6 Newton force pushing these two. And then lastly, you do the same kind of process. I need some kind of force to accelerate a 1 kilogram block at 2 meters per second. So this is going to be 2 newtons. And so the biggest force is always going to be the one that accelerates everything, where each individual force is always going to be less than that. And so that's kind of a good lesson for this one, is that you do want to look at how these individual forces translate through that system. Now our next question is the classic Newton's third law problem. How much tension is in this string right here? Well, let's do this. Let's take a look at this object right here. That 4 kilogram mass. That 4 kilogram mass would have a free body diagram that looks like this. There's a force of gravity pulling down, and there's a tension pulling up. And this thing is in, it's not moving, so it's in equilibrium. So if I looked at this, then the tension in the string would have to equal the force of gravity pulling down on that object. Well, that's just mg, and so 4 times 10 is 40 newtons. Okay, so 40 newtons is pulling on this string right here. There's 40 newtons in that string. Well, if you did that same free body diagram on the other side, you'd also have 40 newtons, because it's not, it's not moving either. So then you say, okay, well, how much force has to be in this string? Well, let's look at a little tiny piece of this string. That tiny piece of string, if I were to just kind of cut out a piece, kind of look at an individual piece, there'd be this force pulling up, translating through, and pulling to the right, 40 newtons. Okay? And there would be an equal and opposite reaction going in the other direction. Okay? And so the question is like, well, how much tension is there? Is there zero tension? Well, no. The end result of all this is that strings can only have one force in them, and that's this tension force. And so if you find the tension at any one point in the string, considering it's a frictionless ideal pulley, then that tension is still going to be 40 newtons regardless. For every action, there's an equal and opposite reaction. That's kind of that trick question that you got to go through and really kind of consider and kind of think about. All right, here's this question right here. It says, which of the following is an expression for the magnitude of the frictional force on the block if it's moving at constant speed? So if it's moving at constant speed, then that means the net forces acting on this have to add up to zero. So first thing I'm going to do typically on these kind of problems is draw a free body diagram. All right, so here's my block. I've got a force of gravity, mg, going down. I've got a normal force going up. There's this applied force, F, acting at an angle of phi. And I also have a friction pulling to the left. And so once you get your free body diagram, what you're trying to understand is that these forces all add up to be zero because it's moving at constant speed. It's in equilibrium. So to make this simple, let's find the components of this applied force. This horizontal component, of course, would be F cosine phi, and the vertical component would be F sine phi. All right. So let's do this. We need to find an expression for friction, first of all. So friction is mu Fn. Okay. Now, mu they give us it's a mu k because this is a kinetic friction, mu k. But they don't give us the normal force. Well, the normal force is not the same as the force of gravity. If I were to come over here and say, well, what's the net force in the y direction? You would say Fn goes up, so that's right there. You also have an F sine theta also pointing up, and you have mg pointing down. And so those added up have to be zero. And so what you conclude is that the normal force is mg minus F sine theta. That's what our normal force is. So this frictional force has to be that coefficient times that normal force, Fn. So we'll multiply this by mg minus F sine theta. So there's my frictional force. And so then you look at it in the horizontal direction. In the horizontal direction, you need to see that this horizontal component, F cosine theta, or cosine phi, has to be balanced by that frictional force, minus F. So the question says, what is the magnitude of the frictional force on the block if it's moving at a constant speed? Well, you could say that the friction is F cosine theta, but the problem is, that's kind of an incomplete answer. It's also true that the frictional force is mu k times mg minus F sine theta. These two terms are actually equivalent. All right. Depends on what the question asks for. If it said, maybe you don't know what F is, or maybe you don't know what theta is, or phi, whatever it is. Depending on which the question asks, both of these would be true. All right. If the speed of an object is moving in a straight line and is increasing at a constant rate, so the speed is increasing at a constant rate. So that means if I were to draw a graph of the speed or the velocity versus time, that graph is increasing at a constant rate. That's a linear increase. And so going back to your kinematics and your graphing of motion, just know that that should have an acceleration versus time graph that is constant. And so therefore, by extension, it says that the net force acting on the object has to be constant. It's not zero, all right? And it's also got to be positive. So speed is increasing, so it means it's being pushed or pulled with some kind of a constant positive force making it accelerate. All right. Next question here shows a couple of blocks, another kind of a system type of problem. So our net force, or our system force, net force on the system, is equal to the total mass times the acceleration. All right. Now it says the acceleration of the two blocks is 4 meters per second squared. So we know what the acceleration is. This is this guy. The force that block Y pushes on block X, that's going to be a force that goes backwards to the left. Well, because there's equal and opposite reactions in these systems, whatever that force is going to be the same as this force right here. All right, so I want to find out what that is. Well, that force, that's the force of X pushing on Y. Well, that's the only force that I can really determine, because kind of going back to one of those previous problems, if I know this force is pushing 6 kilograms, this force only has to push 4 kilograms. So that F equals XY is going to be the mass that this force is pushing times its acceleration. So that force is pushing 4 kilograms and its acceleration is 4. So that's 16 newtons. And that's going to be the same as the force with which block Y pushes on block X. Fy to X. Now while we're here, let's go ahead and figure out what F actually has to be. This net force pushing on F. F has to be 6 kilograms times 4, which is 24 newtons. So that's the total force F. That's that guy right there. Alrighty. Our next question is kind of a good old kinematics force combo kind of question. We've got a 20 kilogram box moving at an initial speed of 10 meters per second, sliding across the horizontal floor before coming to a stop. So what is the coefficient of friction between the box and the floor? All right, so let's do this. We need to find the acceleration. So I'm going to use some kinematics. I've got initial velocity is 10 meters per second. Final velocity would be 0. Delta x is going to be 25 meters. And so if I use this kinematic equation right here, I can solve for A. And when you rearrange the equation and solve for A, you get v squared minus v naught squared over 2 delta x. Substitute your numbers in and you get an acceleration of negative 2 meters per second squared. And it's negative because it's slowing down, it's being decelerated. So if I want to find what the friction is, well, there's only the frictional force acting on it in a horizontal direction. If I draw a free body diagram, it's moving to the right. Sure, there's a normal force going up, a force of gravity going down, but as it's moving to the right, the only force is the friction that's acting down here at the bottom on the surface. So horizontally, F, the frictional force, is equal to ma. And so the mass is 20, the acceleration is -2, so that means our frictional force is -40 meters per second squared. Now that I know the frictional force, I can use the fact that the frictional force is equal to mu times Fn, which is going to allow me to solve for mu. Mu is the frictional force divided by the normal force. Frictional force is -40, or is 40 meters per second squared. We can just leave off the negative sign. And the normal force is going to be the same as the weight, which is mg, which is 20 times 10, which is 200. So 40 divided by 200 gives us a coefficient of friction of 0.2. That's this question right here. All right. Now the next part of the question says, which of the following best describes the frictional forces exerted on the block and on the floor while it's sliding? So there's actually kind of, when you look at it, as this thing is moving to the right, yeah, there's a frictional force that opposes that. That's that kinetic friction that we're talking about, Fk. But that's the friction of the floor onto the box. I can't write today. Well, Newton's third law says that for every action, there must be an equal and opposite reaction. And so that means that the force, the frictional force of the box on the floor is equal in magnitude, but in the opposite direction. So that's the statement that you need to make. All right, this is a good little question talking about pulleys and ropes. You've got this system of pulleys, and it asks you to know what is the spring scale reading. So let's break this down. Let's look at a free body diagram just on the weight itself on this box. So right now there's a weight pulling down on it, and if you look at it, yeah, there's a pulley here, but the pulley is supported by 1, 2, 3, 4 strings. So there's actually 4 tensions pulling up. And usually on these pulley systems, you assume the pulleys themselves have negligible mass, no friction, everything. It actually even says that right there. So these 4 tensions are actually all going to be equal. And so that means that each rope, each string supports 1/4 of the total weight. All right. So now that I know what the tension is, now I can focus on right here on the spring scale. Sorry guys, got you off screen there. All right, so right here, let's focus on this little point. Well, that spring scale, that little pulley or whatever, is being supported by the spring scale. Okay, so it's kind of holding it up. It's whatever that spring is doing, it's pulling up on it. And there's 2 strings pulling down on that particular pulley. So that means that there's a tension down and another tension down. Well, since each tension is 1/4 of the weight, then that means that the spring scale has to be supporting both of those. And so that's 2T, which is 2 times the tension, which is 1/4 of the weight. So 2 times 1/4 is just 1/2 the weight. So that's how much that spring scale would read. All right. Next question. Object is dropped from rest, and it's going to reach terminal velocity. So let's just kind of sketch this thing in stages. So let's say we say it like at t equals 0, right when I drop it. Well, the only force acting on it right when I drop it is the force of gravity, right? So it starts to accelerate at 9.81 meters per second down, meters per second squared down. So that's the initial point. But if I look at it a little bit time later, it's going to be falling down some. The force of gravity hasn't changed, it's still the same, but there is now a drag force that has slowly start to pick up in magnitude. And the reason why it starts off is because it's dependent on the velocity. The faster it's going, the stronger this force gets. So a little bit later, that drag force is going to be even bigger still. And then until eventually, when you get to the very end, when it's reached its terminal velocity, the force of gravity will equal the magnitude of the drag force. These two things will be exactly equal. Sorry, guys. This is what happens at terminal velocity. And so that means the solution to this multiple choice question says the magnitudes of the gravitational and drag forces are equal. Guys, I apologize for the banging. We've got some construction around here. Alrighty, next question. We've got a student with mass 50 kilograms standing on an elevator. Alright, so let's just say this elevator platform is stationary. And in this case, there is 50 kilograms pushing down from that person, his weight, down. And so that means that the force of gravity is going to be 50 kilograms times or 10 meters per second squared. So there's 500 newtons of weight pushing down on that stationary elevator. All right, so now let's say that that elevator platform is accelerating down. All right, so that means that maybe you push the button and the elevator starts to go down. This is just initially, right when you start, it starts to accelerate down. So in that case, I have to look specifically at a free body diagram now. I've got 500 newtons of gravity going down, but the normal force is not going to be supporting that. All right, so the normal force in this case is going to be the force of gravity minus ma. And so when you feel lighter weight, your 500 newtons minus some acceleration times your mass, it's going to take away some of that value of what you feel. So that normal force actually makes you feel lighter weight. And so that's why you would have a 400 Newton reading on a scale, because you've got some kind of an acceleration that has kind of almost made the floor fall out from underneath you. And so that's why we know that this thing is moving down with an increasing speed. You're accelerating down. That's why you feel lighter weight than your actual true 500 newtons. As I apologize, I keep forgetting to move that. All right, moving on. This next question, a little bit of a trick question. You got a bunch of stuff going on here, blocks moving back and forth, tensions, everything. It says the blocks are at rest relative to each other, so that means they're kind of stuck together. They're moving as one system, okay? And they're moving at a constant speed relative to the frictionless surface. So this entire system is at a constant velocity. So if that's true, then that means that the net force on the system is equal to 0. So the only way for that to be true would be for the forces that are applied to it, tension 2 and tension 1, have to equal 0. So if I did a net force equation, you would say tension 2 minus tension 1 equals 0. And so therefore tension 1 and tension 2 are equal to each other. That is the relationship between T1 and T2. Now it says the force of friction experienced by the top block is F1, and the force of friction experienced by the bottom block is F2. What is the relationship between these two? Well, once again, if you've got force 1 and force 2 applied to both these blocks, it says that they're not moving with respect to each other. So that also means that these two forces have to be equal, since there's no relative motion. between them. They kind of cancel each other out. All right. Okay. Oh, getting close to being done. All right, so we've got another system with a 15 Newton force pushing on this cart with a block on top of it. There's no friction between the surface, so this surface down here is essentially frictionless. No friction in the wheels. It doesn't say it exactly, but you would assume that the wheels have no rotational inertia, no appreciable amount. The coefficient of friction between the cart and the block right here is static friction, so it's 0.7. And the block does not slide on the cart, so that means that these two things are stationary relative to each other. Find the magnitude of the horizontal component of the force that the block exerts on the cart is nearly. So what we're trying to find is how much force this cart pushes on this block. How much force does this cart push on this block? Well, it's got to be some kind of a frictional force to cause it to move. So first thing we need to do, let's just start at the beginning. F net is equal to ma. So therefore A is F net over m. And so what I'm trying to find is the acceleration of the system. So that'd be 15 newtons divided by 3 kilograms. So that means the entire system is accelerating to the right at 5 meters per second squared. And so if that means that the top block, not the cart, but the block, also has to be accelerating at 5 meters per second squared. Well, in order for that to be true, there has to be some force accelerating it to the right. And that force is going to be the frictional force that the cart provides to the block. So that frictional force has to accelerate a 1 kilogram block with some acceleration, and that acceleration is 5. So 1 times 5 is equal to 5 newtons. That's the magnitude of the horizontal component of the force that the block exerts on the cart. And the reason why it's going to be the same is because equal and opposite reactions say that the block is going to exert the same amount of force on the cart. All right. Okay, so here's a car going around a curved track. Let me just kind of make this kind of neat. So here's a curved track right here. It has a radius of r. It is going with a speed of v naught. So let's just say this thing has a speed, tangential speed v naught. Says the coefficient of friction between the tires on the road is mu for the car to not slide on the road, which must be true. Well, if I look at the force on this car going around the track, that frictional force between the road and the tires has to be pointing inwards. That's a centripetal force pointing inwards. So therefore, if I go back and look at centripetal force, it has to equal ma. Well, I'm saying that the centripetal force is the friction. So that has to equal mac. Well, friction is mu Fn, where Fn is mg. All right. The mass times the centripetal acceleration. Well, the centripetal acceleration is going to be v naught squared over r. And so that means that when I bring all this stuff down, the mass term cancels, and we're left with, bring that back up here, we're left with the fact that mu times g must equal v naught squared over r. Okay? And so if I rearrange this equation and solve for r, the radius has to be greater than or equal to v naught squared over mu g. And that's one of our options here, choice D. The radius cannot be less than v naught squared over mu g. It can be equal to, but it can't be less than. All right. So our last couple of questions. Here we've got a block. What is the approximate magnitude of the force of friction as it slides down the incline? All right, so this one, let me sketch out a free body diagram. So here's our incline. It's at 37 degrees. Here's our 2 kilogram block. If I draw my forces, I'm going to have a force of gravity going down. I'll just label it as mg. I've got a normal force perpendicular to the incline. That's going up, perpendicular. There's also going to be a little bit of friction uphill. Okay, and so when I break up my normal or my force of gravity into components, there's a component that opposes the normal force. That's going to be mg cosine theta, theta being right here. And then there's also going to be a component that goes downhill. That's going to be mg sine theta. All right. So let's draw a net force equation for the horizontal direction. So in the x direction, and guys, when we do this, remember the horizontal direction, I'm really meaning in the direction that it's accelerating. So it's accelerating down this hill. That's going to be my horizontal direction. All right, so Fx is going to be, or net force in the x direction is going to be mg sine theta minus the friction, and that has to equal ma, because it's accelerating down this hill, acceleration down the hill. So rearrange this equation, solve for f. F is going to be ma minus mg sine theta. Is that right? Let's see, mg sine theta. Okay, no, it's going to be plus because they're adding together. So that means that the frictional force will be, I can factor out the m, I guess. Acceleration. Actually, no, it is subtraction. I'm sorry. They are subtracted from one another. It's going to be ma minus g sine theta. And so the frictional force has to be 4 newtons. I'm going to substitute newtons. I'm going to substitute that acceleration in there. All right. And our last question, this is a classic static equilibrium problem. I've got two tensions at equal angles pulling up, so they're going to be the same tension. I've got force of gravity going down, mg, and so when I break these tensions up into components, the horizontal components are going to cancel. The vertical components will be t. In this case, the angle's up here at the top of this little triangle, so these are going to be the adjacent sides. So it's going to be t cosine theta, t cosine theta. And so therefore, when you sum the forces in the vertical direction, you have 2 t cosine thetas minus an mg, and that has to equal 0. So 2t cosine theta is equal to mg. So solving for t, you get mg divided by 2 cosine theta. And that's your solution. All right, guys, that concludes this video. If you have any specific questions, just email me or post it on our new Google Classroom page, and I'll be glad to help you out. Thanks a lot, guys, and have a good afternoon. Bye-bye.